So let's get going right into our panel discussions, and I know we're a little bit behind, so we'll give you the full hour and we'll kind of catch up as we go through the day. So thank you again very much to our sponsors for the day, or our sponsor for the day is Northrop Grumman, but also sponsoring this session is Teledyne Braun Engineering. This session is moderated by Dana Issei. Dana is the Deputy Manager of the Science and Technology Office at NASA Marshall. Dana.
Thank you. Good morning, everyone. So today we're going to be discussing exploration enabling science. We have a great panel. So the way this is going to work for this panel is I will introduce our scientists. They're going to each do a quick presentation on their particular area of study. And then we will do questions. We'll take questions from the audience, and then I have some questions to ask them myself. So let's get started. First, we have Dr. Deborah Needham. She is a program scientist in NASA Science Mission Directorate, Exploration Science Strategy and Integration Office, where she works to integrate cross-disciplinary science into exploration of the Moon and Mars. Dr. Needham trained as a planetary geologist, studying volcanic and impact features on all planetary bodies in the inner solar system, before transitioning to her exploration integration role for science. In SEO, she has led coordination across SMD and the science community to define the agency's Moon to Mars science objectives, and she has worked across multiple platforms to define science needs for exploration architecture elements. Next, we will have Renee Weber. Dr. Renee Weber serves as chief scientist at the Marshall Space Flight Center. Her research focus is planetary seismology, and she's held active roles in multiple planetary missions, including the InSight geophysical station on Mars and the GRAIL lunar gravity mission. Dr. Weber's role at Marshall is to provide advocacy and strategic leadership to the formulation, maturation, design, development, and operation of research and technology projects within the Multidiscipline Science and Technology Office. She also supports the Artemis Human Landing System program, representing science and utilization, and has led the Artemis III Science Definition Team on behalf of the agency's Science Mission Directorate. Then we will have Dr. Brent Denevy. She is a planetary geologist at the Johns Hopkins Applied Physics Lab and is the principal investigator for the Artemis III Geology Team. She has been a member of numerous NASA robotic mission teams, including 4 ongoing or upcoming missions to the Moon. She's the deputy principal investigator of the Lunar Reconnaissance Orbiter Camera, co-investigator on NASA's ShadowCam instrument on the Korean Pathfinder lunar orbiter, instrument lead for the cameras on Lunar Vertex, and co-investigator on Lunar Vice. And then we will have Dr. Edward Bierhaus, Bo Bierhaus. He is a principal research scientist at Lockheed Martin, engaged in both planetary science research and mission implementation. He has 25 years of research experience studying objects across the solar system, including the Moon, Mars, icy satellites, and small bodies. He has 20 years of mission implementation experience, including lead scientist for the OSIRIS-REx sampling system. He is science co-investigator and lead of the Geology Working Group for NASA's Lucy mission, which launched in October 2021. So thank you to the panel for being here, and we will start with Dr. Needham.
Good morning, everyone. I've got to start by saying what an exciting time to be a scientist of space. We have kicked off the year of the sun with our first of 2 solar eclipses and the closest approach of the Parker Solar Probe to the sun, and closing with the science community's definition of what exciting science objectives we want to achieve for the next decade. We also have the autumn of asteroids with the recent return of the OSIRIS-REx samples, an upcoming close encounter with, from the Lucy spacecraft, and the recent launch of Psyche. There's so much exciting science happening. We also, of course, have the most state-of-the-art technology and telescope for the Webb telescope up in space right now, looking deeper into the history of time than we've ever seen before. And then we have the upcoming first landings of the CLPS, Commercial Lunar Payload Services companies, delivering our science payloads to the surface of the Moon over the next couple of months. So we have such an exciting time for science. And NASA, as an agency, has embraced how important it is for science and to help enable exploration and for exploration to enable science. NASA has indicated and embraced that science is one of the key reasons for why we are exploring, with the establishment of our Moon to Mars objectives. So that's one of the key talking points to talk about today, and questions that you might have for us. But talking through the Moon to Mars objectives for science, there are multiple segments of those Moon to Mars objectives, but I wanted to focus on the science, of course, because this is a science panel. But those are multidisciplinary, crossing across all of the divisions of science, including, of course, from the SMD perspective, planetary science, heliophysics, biological and physical sciences, and also the fundamental physics and astrophysics. But they also include, from the other science operations, space operations mission directorate, the human research objectives as well. So these objectives we've worked across the different science communities, across our different institutions and commercial institutions, and our international partners to hone those objectives to make sure that we are all exploring together as we establish why we're going, why we're exploring Moon to Mars, but also how we're going to achieve those objectives as we design this architecture going forward. Then NASA is also trying to be as transparent as possible with our plans for the future to encourage investment and excitement across all of our partners, whether they're domestic institutions, commercial, and international partners, as the agency publishes our architecture definition document, which is an annual release of what NASA's plans are as a snapshot in time. That plan was first delivered and published last year, or at the beginning of this year, actually, I should say, in the January timeframe. And every year we go through as an agency to conduct studies and trades that mature that architecture definition. And so the next iteration of that document is going to be coming out early next year. And we have, over the last 2 years, and continue and plan to do so in the future, engage our partners across the world to get feedback on that definition, on that architecture, so we can all invest together and accomplish the amazing science objectives that we want to achieve on the surface. So with that, I will send it over for more specific science definition with my colleague Renee Weber.
Yeah, so I'm going to talk a little bit about those science objectives and how we, did I break it? I don't see it over there. Okay, I'm just going to wing it then. Oh, there we go. And how the agency plans, to distill those kind of high-level objectives down to actual activities that the astronauts will perform on the surface of the moon. And to that end, the Science Mission Directorate actually chartered a science definition team to help essentially perform that activity, which was back at the end of 2020. And so the team was essentially charged with defining compelling and executable science objectives for the Artemis 3 mission. And, this team wasn't really the first group of people to ever think about doing science on the moon. And so the first thing that we had to do was essentially try to distill all of the remaining, the large remaining unknown science questions that are outstanding that we need to go there to gather new data to address. And fortunately, we have a large variety of community consensus documents that are put together by different advisory groups that we drew some very high-level objectives from. And so there are 7 high-level science objectives that we are focusing all of our activities towards. The first is understanding planetary processes. The second is understanding the character and origin of lunar volatiles. That's a big part of why we are going to the pole of the moon, which is where those materials are concentrated. The third is understanding the impact history of the Earth-Moon system. The fourth, and I'm starting not to be able to see them so well. Let's see, the local space environment. Fifth is understanding the universe. So that's essentially using the moon as a platform. And the sixth is taking advantage of the unique environment of the moon to perform science that we can't do on Earth or on the ISS. And the seventh is investigating and mitigating exploration risks. And so that is the area where we look at the overlap between science and exploration. And, you know, one of our pillars is having science and exploration sort of mutually benefit each other. So the science definition team took those top-level objectives and then performed a traceability exercise where we mapped those down to a group of goals, and then from those goals, we looked at a specific set of investigations that would address those goals. And then we underwent a prioritization activity where we had to figure out, you know, which of these do we think, which of these are still important questions to address that we haven't made any progress on, either with reanalysis of data from Apollo or with new missions to the moon. So those were sort of the highest priority from a science perspective. And then we asked which of those can we address specifically with the Artemis 3 mission architecture and what we knew about it at the time. So, you know, a polar mission, about a week long, where we have 2 crew who are going to be doing however many, you know, 4 EVA, up to 4 EVAs, and they're going to last this long. So we take all of this information and we use that to essentially build a campaign that we think will best address those science objectives. And so for Artemis 3, the campaign that we arrived at was sort of a 3-pronged approach, where we have sample collection and return, we have in situ field science and field geology, and we have deployed instrumentation. And so, you know, the report made a recommendation that described that campaign and then essentially gave that report to NASA, who's then, you know, sort of responsible for dealing with the implementation. And so, you know, we're pushing forward. Right now I'm working on helping implementation on the deployed instrument side. And Brett Denevi and her team have been brought on to look a little bit more about the geology aspects. And so I'll turn it over to her to talk about that.
Start with turning that on. Okay. So as mentioned, I have been recently selected to lead the Artemis 3 geology team. We have an amazing team that includes 12 scientists from across the country, as well as UK and Canada. So our team, as was defined, you know, the kind of work we'll be doing, we have a really incredible privilege to set the lunar science objectives for the Artemis 3 mission. So this is pulling from all of the work that Renee did with the Artemis 3 science definition team. Our team includes members of that team, and as well as the planetary science and astrobiology decadal survey, and the kind of goals that the lunar science community has put together for many years. You can imagine we have been waiting for some time to get back to the lunar surface, and so we have a lot of goals and a lot of objectives. But now we'll be focusing those on specifically which can be achieved within the constraints of the Artemis 3 mission. So we'll be planning the surface science activities that the crew will do to accomplish those science objectives. We'll support the real-time operations as the mission is ongoing. And then we will make the kind of first pass effort to do the preliminary examination of the samples, all the data, everything, pulling that together to synthesize it into what have we learned. Our overall team goal that we have come up with is that we want to maximize the science return of Artemis 3 and ensure the samples and data that are collected are going to enable science from the science community for decades to come. So we are helping get this job done, but then the samples, the data, the science, it will all be there for the world's science community to continue to make progress on these goals and objectives for many, many years, as we are still seeing with the Apollo samples. I'm pushing a button. too far. Okay, thank you. So our Artemis 3 goals are a sort of a distillation of those that Renee talked about. Each of our goals are more focused on the geology science, so of course, and from these we'll have more specific objectives that as we constrain the landing sites further, we will see how those can be accomplished. So the 4 areas that we are focusing on is understand the early evolution of the moon as a model for rocky planets. So this is one of my favorite topics because so much of what we know about the very earliest evolution of planets comes from the moon because Earth's earliest history is not well preserved. So really in order to go back and understand how do planets form, how do they differentiate, how does a crust form, how does that crust evolve over time, that earliest record is really most accessible to us on the moon. We'll determine the record of inner solar system impact history. One of the biggest goals for lunar science for some time, and for planetary science as a whole, has been to understand the very earliest bombardment history. We think there was a large peak in impacts, or either a declining trend of impacts around 3.9 billion years ago. And the timing of that is really important because that is when we think life was first evolving on Earth. So understanding that impact record, how intense it was, and how that shaped the habitable environment of the Earth, because all of the impacts that were hitting the moon, that same population of impactors was also hitting the Earth. So we'll work to constrain that, and a lot of the landing sites near the South Pole are really key for that because they are on the rim of one of the oldest and largest impact basins in the solar system, the South Pole Aitken Basin. So we're hoping to be able to get samples that will inform our knowledge of that basin and its formation. We're exploring the regolith in the area. That's just a kind of fundamental understanding of how that surface is formed, how does it evolve, because all of the samples that we will be getting are not going to be in situ rocks that come from an outcrop. They're going to be ground up rocks that have been affected by billions of years of the impact environment. And then, of course, one of the keys to the South Pole is this will be our first chance to bring back samples that may contain some of those polar volatiles. So understanding that record and what we can learn about the origin of those volatiles, that's the part I'm excited about. Were they delivered by comets, asteroids, the solar wind, early lunar outgassing? And then, other people are much more excited about how much of them are there that we can use for potential resources for future exploration. So we will be doing all of this work to kind of push this science forward and evaluating the landing sites in terms of their potential for answering these questions and how we can best use the really key resources that we have on the Artemis 3 mission, which are the crew time and then the sample return mass to really maximize the science that we can get out of Artemis 3. And one of our goals is to bring the whole community along with us, so we're going to make sure that all of the data is put out quickly and is accessible for everyone. So, all right, thank you.
Good morning. If you're looking at the slides carefully, you might notice it's not the moon. And you might be wondering why we're talking about asteroids, and I promise I'll talk about the moon in just a second. So I'm showing examples of 2 asteroid missions on this slide, and if I get the orientation right, yep, so my left is your left too. So on the left is OSIRIS-REx, and on the right is Lucy. And as noted in the introduction, I was the lead scientist for the TAG-SAM, which is the sampling device on OSIRIS-REx. And if you count the proposal phase, which goes back to 2004, it's been a pathway 19 years in the making. In the background, you'll see a global mosaic of beautiful asteroid Bennu in all of its rocky glory. That was acquired by one of the visible imagers on board the spacecraft. In the upper right is a series of spectra from both meteorites that were collected on Earth. Those are the different colors, and then the Bennu spectra, which was collected from one of the spectrometers, is the black on the very top. And admittedly, it's a bunch of squiggly lines, so I don't expect you to really pay attention to them too much, but they, trust me, really are very exciting squiggly lines. Because there's a dip that is helpfully annotated by a vertical line there, and that indicates the presence of hydrated minerals. And water on an asteroid is a pretty cool thing. There are other spectra to indicate that Bennu was carbon-rich. And the great thing about remote sensing and these squiggly lines is you can get a sense of composition, but you don't really know the details unless you actually have sample in your hand to analyze and to examine in detail. And so the picture in the bottom right of the OSIRIS-REx is the TAG-SAM. It's pretty remarkable to spend a long time working on some hardware that you send into space, collect a sample, and bring it back, and then see it in the clean room. You might be able to see, it's a little small in this rendition, but there's some Bennu sample sitting on the sample head itself that's visible. And so the analysis part of the mission has already started. The science team has done some quick look analysis, and if you happen to watch the press release or the press event a week or so ago, initial analysis has in fact confirmed that, yep, it's got water and organics, and in fact, it's one of the most organic-rich materials that have been returned beyond Earth. So it's a pretty remarkable achievement and a pretty remarkable science result. On the right is Lucy, and it's actually not the spacecraft. It's a diagram of the solar system, but it's just kind of to orient you to the targets. Lucy is going to the Trojan asteroids. And if you haven't heard of them, that's okay. That's what this diagram is here to explain. So Earth and Mars are there, and then in between Earth and Mars is the main asteroid belt. You're probably all familiar with the asteroids that live between Mars and Jupiter. I may have misspoken there earlier, but yes, the main asteroid belt is between Mars and Jupiter, and then the yellowish tan dots are the Trojan asteroids, and they lead and trail Jupiter by 60 degrees. They don't actually orbit Jupiter. They orbit the same distance from the sun as Jupiter, but for those of you that are up to speed on your restricted three-body problem dynamics, they sit in the Lagrange points, so the L4 and the L5 Lagrange points with Jupiter. And if you remember that math, you remember that those points are very stable. So if you put something there, those objects will stay there. And so in some sense, it's not a surprise that those asteroids are in those locations, because Jupiter and the Sun are the two most massive bodies in the solar system by far. So if you expect the restricted three-body problem to work anywhere, it would work with the Sun and Jupiter. But the tricky part is getting objects there in the first place. It's actually hard to deliver objects into these L4 and L5 points. So one of the big questions of the Trojans, but also of the solar system, like the architecture of how you distribute mass across the solar system, is how you ended up with the Trojans. And the cool thing about the Lucy mission is Brett was just telling us about the late heavy bombardment in the inner solar system. And one of the explanations for how you get the late heavy bombardment is that the giant planets actually formed in a more compact configuration than they are now. They migrated out. They interacted with what's known as the Kuiper Belt. They were swinging their gravitational baseball bats willy-nilly, sending small bodies out of the solar system, but also sending small bodies into the solar system, to the inner solar system, and hitting the Earth and the Moon. And that also is a mechanism by which you can deliver Trojan asteroids to their L4 and L5 points with Jupiter. So there's this interesting connection across the solar system where you maybe have outer solar system objects that are now orbiting at the same distance to the sun as Jupiter, and part of their companion population is some of the bodies that ended up hitting the Earth and the Moon and other inner planets 3.9 billion years ago. So it's telling us that the solar system is perhaps one, more dynamic than we ever thought if you have giant planets that are migrating, and two, that the whole solar system is connected. We have stuff that probably formed in the outer solar system coming in and hitting the Earth and the Moon. So pretty remarkable science that's happening from these two asteroid missions. And so I told you I'd get back to the Moon, so now back to the Moon. Why is this important? Well, before Apollo, there was almost a decade of robotic exploration. There were multiple lunar orbiter missions, there were multiple lunar surveyor missions, because some of the most basic properties about the Moon were unknown at the time. It's hard to think about now, the classic astronaut boot prints on the Moon, and we know so much now because of LRO and other missions in the past decade. It's hard to remember a time when we didn't have as much knowledge as we do, but before the first missions went there, we had no idea. There are some anecdotal evidence about speculation that if you tried to land on the Moon, you would just sink deeper and deeper into the surface. Or there was a thought that all of the craters were perhaps volcanoes, and some, a volcano might, damage the astronauts. And all of this was unknown, right? And so there had to be these robotic precursor missions to make these fundamental measurements. And they provided not only critical science to help us understand the Moon, but they also provided critical data to design missions to enable astronauts to land safely and come back safely. So these precursor missions are critical for establishing the mission profile and the architecture that's needed for the astronauts. And so these examples of OSIRIS-REx and Lucy are precursors for obviously a time when we might go beyond the Moon, but also the techniques. Obviously, a big part of the Artemis mission is sample collection and sample return. And there are differences, of course, between collecting a sample on an asteroid and collecting a sample on the Moon, but there are a lot of similarities, things like cleanliness. Making sure that what you're measuring is the sample itself and not terrestrial contamination. So working on techniques for understanding how to collect a sample, keep it clean, and then be able to analyze it is all stuff that is relevant whether you're collecting sample from an asteroid or whether you're analyzing lunar samples. On the case of Lucy, Lucy's first flyby is actually next week, but it's not of one of the Trojan asteroids, it's a main belt asteroid, and that flyby was not originally a part of the mission plan. It's serendipitous. We found out after the spacecraft launched that we were going to be flying by a main belt asteroid and that it would just take a little maneuver to get us close. And one of the huge benefits of astronauts is they can do serendipity science. And so by practicing it with robotic missions, also being able to practice with flybys, is a way that Lucy is helping us, again, build that infrastructure, not only from a technical perspective, but also from an operational perspective. So it's a combination of the amazing science that we're getting from these missions that are laying the groundwork for discoveries of the solar system, but it's also laying the groundwork for human exploration across the solar system. And so I'll just wrap up by saying that robotic exploration and human exploration have always gone hand in hand, and it's essential that they continue to go hand in hand because they're extremely complementary and fundamental to one another.
All right, great, thank you. So we'll start with questions. I'll do a couple, and then we'll let the audience ask a couple. So from the presentations, obviously, Artemis 3 is really where the science campaign starts. So I would ask each panelist, what science are you most excited about in Artemis 3? Except for Dr. Denevi, who already said that she was most excited about volatiles. So she can tell us her second or 10th most exciting thing happening. So Dr. Needham.
Oh, it's like picking my favorite child. I mean, part of it is just getting our hands, gloved hands, dirty on the moon again, and getting those boots on the regolith. I think that stands to be such a monumental achievement. I know, we went to the moon 50 years ago, but doing it today with all of the new systems and the new paradigm of how NASA's approaching exploration I think it's going to be really exciting to have that achievement. For science, I mean, I think, Brett covered a lot of the amazing science that we're going to achieve. I think for me personally, the most exciting is to establish that earliest chronology. I think that is one of the key. We use the moon as a cornerstone for the rest of the solar system for our understanding of not only the origin and evolution of life and when that happened, how that happened, and what was the environment for that. But that's one of the science objectives that we currently cannot do from remote observations. We can't understand the age. We need very highly precise technical instruments on Earth, or room-size instruments that are required to get the right precision that we need to get that answer. So that's one of the objectives that I'm most looking forward to resolving.
Okay, good. Dr. Weber?
Yeah, that's, again, a difficult question to answer. But, my background is in geophysics, and so, I have to admit that I'm most excited about the potential for new deployed geophysical instrumentation on the moon. I looked at data from the Apollo missions for my PhD research and for the foundation of my scientific career, and, for a decade, the last sentence of every paper or abstract that I ever wrote was, we really need to go back so that we can answer this question more fully. So finally having the opportunity to do that is, it's incredibly exciting. It's a great way to, like Bo said, kind of leverage the unique advantages that astronauts have to get us information that will ultimately end up being useful to plan for future human exploration. So that's what really got me excited.
Yeah, and I think one of the biggest opportunities is going to come from the fact that the Artemis crew will be exploring an area that is so far from other areas that have been really explored with crew, or even in depth with samples brought back robotically. The near side of the moon is weird. It is geochemically unique. It's elevated in heat-producing elements. It's really different than the rest of the moon. And so a lot of what we've learned about the moon has come from an area that's maybe not fully representative of the processes that have shaped the entire moon. So I'm really excited about the prospect that we could find out what we've gotten wrong. The late heavy bombardment is a theory, and it's actually pinned down to a lot of evidence that comes from those samples collected on the near side. And there's been a lot of work, really since Apollo, but even more so in the past 10 years, showing that we don't know that we actually found a lot of different impacts all occurring late. 3.9 billion years is kind of late for large impacts, because by that time, most of the solar system should have, quieted down. There shouldn't have been as many large impactors flying around. The big debris was swept up through, planetary accretion. So how did you have this huge spike late? And we've explained it in all of these really interesting ways, but we still don't know for sure that spike in impactors happened. And so we may have been sampling the same one large impact over and over again and interpreting it as a spike. So I think that, for me, would be really exciting. Either way, we'll show that was a real spike. It was a huge event in the solar system-wide influence and course of events. or, we'll find new evidence for a different impact history, and we'll have to reevaluate all of our theories. And so that fundamental science and change and option for overturning paradigms is what gets me really excited.
What they said. Yeah, it really is hard to narrow it down because the science is so sweeping and so vast and so profound. Because volatiles on the moon, water on the moon, you've got this desiccated, dry, not quite hard vacuum environment, and yet somehow there's this volatile-rich deposit in both the South Pole and the North Pole. So figuring out how that got there and how universal is that process, right? So we know that from the measurements, we expect that there's water there, but we still don't know specifically the distribution of the physical water. We don't know the kind of water. And one of the interesting questions is, if this is happening on the moon, does this happen elsewhere? And I think there's some evidence on Mercury, for example, that Mercury might have some of this at its poles. What's the smallest body where you could get polar volatiles? Could this happen on some asteroids in the main belt? Could this happen on some dwarf planets in the main belt? So by making these measurements at the moon that are new, you're, again, not learning just about the moon, but you're also learning about processes that could be extrapolated across the solar system. And then I think, yeah, it's important to come up with hypotheses, and it's important to come up with specific objectives because that allows engineers to design the mission and come up with requirements and do those sorts of things. But sometimes the most exciting discoveries are those things that just come at you from left field that you had no idea. And we have an amazing abundance of Apollo samples, and they have told us a huge amount about the moon and about the Earth as well. But they have been from a fairly limited cross-section of the moon. And one of the things that some of the orbiters are showing us, especially with high-resolution data, is that the moon is far more complex than we had originally thought. And again, I'm going to speak about an asteroid for a second, but bear with me. So Bennu, the asteroid that we went to with OSIRIS-REx, asteroids are dead. They don't have volcanism on an asteroid. What are you, crazy? But the estimated surface age of Bennu is something like a few million years old. And to put that in context, in geologic timescales, that's nothing. Dinosaurs went extinct 65 million years ago, and we're looking at a surface age on a small dead asteroid that's just a few million years. So the solar system is awash in processes that exist that we don't understand because of our terrestrial biases. And so by virtue of going somewhere new and taking new data and collecting new sample, we get outside of our realm of expectations, and we can learn something totally new. So I think, definitely the volatiles, definitely the chronology, and then definitely stuff that we can't even think to ask questions about right now.
Okay, great, thanks. I think at this time, I'd like to see if there's any questions in the audience. I think there's a microphone.
So we're focused on Artemis 3, which is good, but do you expect the science goals or even EVA operations to change drastically based on what we learned from early CLIPS missions or Starship Uncrewed Demo, Artemis 3, or these asteroid missions?
Yeah.
I'll start and hand it off. We learn something new every time we take another measurement. I mean, LRO is orbiting, and when we send CLIPS landers to the surface, the data that we get back is absolutely going to feed what we want to accomplish. I will say that many of the objectives that have been established by the science definition team and underscored by the geology team have been around for 50 years. Some of these objectives we have to get samples back to address them. We have to carefully and strategically place instruments on the surface, and some of those really need crew handling and place them correctly. We've demonstrated that robots can do a lot on the surface. InSight on Mars deployed a seismometer, and they've made some phenomenal achievements and measurements on Mars. So we can do some things with robots, but having humans in the loop is critical to achieving some of these objectives, and bringing samples back is critical. So I expect that at least for Artemis 3, those objectives are going to survive any robotic missions at this point.
Yeah, I would agree. The objectives, at the highest level, those 7 Artemis science objectives, those are really intended to capture every question that we could feasibly think of that could be addressed on or of the moon. But, on a mission-to-mission basis, I would say that, how we prioritize which of those, which investigations we're going to do and how they map to those objectives can definitely be, replanned based on the information that we have in the moment. So if in the next few years, Eclipse lander made some progress towards a fundamental outstanding question, then we can maybe reprioritize what we're thinking for future missions, whether they're human or robotic, based on those findings.
Yeah, I'll just add, I think the objectives and the overall science goals are they will stay largely fixed, but what we learn about how to implement them most effectively will likely change based on, initial results we get back from Artemis 3 can then help reevaluate where we want to best go. Or even, Viper is going to robotically explore permanently shadowed regions, give us the first information about volatiles in PSRs in situ. And so that will likely inform how the geology gets implemented to sample those, what type of spot you might want to go, what the terrain is like in those permanently shadowed regions. So we'll learn more and more about how to best implement the science, I think.
Yeah, I think the interesting thing about the moon is that from an operational perspective, a lot of it is latitude driven. Your power profile, your thermal profile, all of those things are very, very sensitive to where you are in terms of latitude. And so when you're building an exploration architecture, you have to have all of this hardware that comes along with you to address those things. And so I think from a hardware perspective, it can be hard to take something that's architected for the South Pole and have it work at the equator or vice versa. So the destination-driven aspect of this, in some sense, unfortunately, has this dependency on the environment of the moon, right? And the fact that the moon can be so different depending upon where you are in terms of latitude. But I think Brett really articulated it well, which is that, even if you have a set of destinations set up, if you're not going to change those destinations, or if you're not going to change it in terms of latitude, at least the stuff that you learn on the first mission, procedurally, scientifically, those sorts of things absolutely have to inform the follow-on missions.
Great, thank you. Do we have any other audience questions?
Hi, I'm Charlie Stegmiller with Leidos, and thank you all for a great panel. With the timeline and delay that sample returns create, what is the work going on for in situ measurement, instrument design and development? Because you could go out to the Trojans, or you could go out and get in situ sample return. Because when you think about the returns today for Artemis, even getting a -180 freezer is going to be a challenge to return a cometary ice kind of sample. So where does the state of the practice, and where are you going with in situ measurements as a technique?
Okay. Who wants to start that one? All right.
Great question. So one of the things that is a fantastic aspect of exploration is the CLIPS and the PRISM program. And I'm fortunate enough to be a part of a PRISM selection that just recently happened, which is going to put an in situ age dating instrument on the surface of the moon. And that's kind of a big deal because we talked about the importance of chronology, but it's also a big deal because it's never been done before. In situ age dating has never happened before in the history of planetary exploration, and we're hoping to do it for the first time with this PRISM activity. It's going to an irregular Mare patch, which is a cool volcanic feature. I can talk to you about it later. So I think there's definitely parallel pathways that have to take place because we are never going to be able to do sample return from every destination in the solar system. It is just impossible to do that. It takes more time, it's more expensive, there's a lot more overhead involved. So absolutely, if we want to maximize our scientific understanding of the solar system, we have to be able to do stuff in situ. So I think there are all sorts of instrument programs that are there to support that activity through the science side of NASA. I will say that in support of sample return, you're never going to, well, I shouldn't say never. It's going to be a long time before we miniaturize a synchrotron, and a multi-kilometer long collider is going to be one of the instrument suites that get applied, has been applied to return samples and will be applied to Bennu. And so there are just certain technologies for doing sample analysis that we can do on Earth that we can't do. So there's always going to be a place for sample return, but absolutely we need to improve our in situ capabilities as well.
Dr. Needham?
Yeah, and thanks, Bo. I know I threw you under there to start, but I wanted you to highlight Dimple. But yes, so there are a number of programs that SMD supports, planetary in particular, for instrument development. So there's the low TRL, Dolly and Picasso, and then there's the high TRL Matisse to get payloads developed and technologies matured in preparation for flight. And then PRISM and CLIPS are an opportunity to demonstrate those and deliver them to the surface. So there are definitely investments being made from a science instrumentation perspective in order to enhance the capabilities that we already have and already are demonstrating on the Mars rovers for composition of various mass spectrometers and infrared and spectrometers and things like that. So there are a number of instruments that can be used in situ to characterize the surface, and I completely agree that the investment needs to continue to develop those technologies for future applications.
Okay, anyone else? I think we have about 10.
All right. In my time, I have read many a project done by NASA and other aerospace corporations related to it. This is not just about Artemis 3, but the program as a whole. What type of robotic missions are not missions, but projects are going to be brought back from a hiatus? Just because one robotic project I have in mind is the Athlete Prototype Rover, which is I believe, a 6-legged chassis that can carry pressurized habitats, cargo, other sorts of payloads. I'm just wondering what kind of specific machines will be brought in the future. Sorry for the off-topic question, but I kind of came in late and I just wanted to know about that.
Yeah, it's actually not off topic. It goes straight into the heart of the architecture definition and development that NASA's been working on. The approach that we're taking now is to define our objectives, and they refer, or I suppose we refer to it as architecting from the right. So what do we want to achieve with the architecture? What are our goals and objectives? And then work backwards from there to deconvolve what do we need to build from a hardware perspective in order to achieve those objectives. So the way it's working is we're defining use cases and functions that are needed in order to achieve our objectives. And then we'll go through those functions and work through prioritizing, well, identifying gaps where we need to develop hardware in order to achieve our objectives, and then prioritize the investments that we make in the development. So it's an ongoing process. I'm going to be a little vague and not necessarily answer your question directly by naming specific hardware, but the process is to figure out what do we need in order to achieve our objectives, and working from those functions, define the hardware.
Okay, thank you. Oh, we had another question.
Yeah.
Yeah.
What are the biggest current uncertainties in the overall architecture for Artemis 3 or the capabilities of components like the lander and suits that are affecting your planning for the science you'll be able to carry out for the mission?
Renee, you want to take that one? Okay.
So, we're working very closely now with our partners to answer those exact questions. Whether it be, designing or planning for the EVAs, what science activities will be done on the EVA, or planning for the payload design, how it will be handled and deployed by astronauts, or where it will be stowed on the vehicle, or how it will transfer data. Those are the questions that we are working to resolve right now. And, we're making pretty good progress. We're working really closely with those teams. We're having, technical meetings and interchanges, and we're working with the crew office to help with crew training that will bring us closer to resolving those questions.
And I can just answer as the uninformed person who is just wandering into Artemis now, trying to learn the answers to these questions. I mean, the things that I think are going to be really important to learn are, what is the downlink capability during an EVA? Will we be able to get crew pictures back right away? How far will communications reach? How long will the EVAs be? These are all things that, I don't know, maybe you all know the answers to yet, but I don't know the answers to. So as the geology team is getting involved, those are the questions that we're starting to try to address.
Okay, I have a question for the panel. So how is what we're going to learn in the lunar geology and with sample return going to help formulate our strategy for Mars? We are the part of the Moon to Mars program under Artemis. So how does what we're going to learn on the Moon help inform what we're going to do on Mars?
Yeah, I'll take this one. It's an excellent question. One of the first things we need to do in order to understand how we're doing on the Moon is applicable to Mars is to define what our objectives are for Mars the next level down from the Moon to Mars objectives. So there's actually a National Academies of Science study that is just getting kicked off now to do just that and address from a science community perspective, what do we want human explorers to achieve on Mars? And once we have that answer, we'll be able to more strategically address and strategize what we want to do on the Moon, specifically in advancement to prepare for Mars. I think, Artemis 3 already, we don't necessarily have those Mars objectives defined yet, but everything we're doing in the human lunar return, that initial segment of lunar exploration, is getting humans to operate and survive and work on another planetary body. And that all is very applicable to Mars. I mean, of course, the hardware specifics are going to change, but the procedures that we develop, and not only for actual crew procedures and what they're doing on the EVAs, but how is science integrating into the ops and into the control center, whether that's in Houston, whether that's in Marshall, for the payload ops, those kinds of connections and processes have to be established. So all of that is going to be relevant for Mars.
Okay, thank you. Anyone else from the panel want to weigh in? No. All right, let's throw it back to the audience. Are there any other questions? We have one.
As an astronomer, besides the obvious geology science and planetary science, what other science projects do you envision eventually taking place on the moon?
So I'll take that, and I think the answer there is, what science can you dream up? The great part, or one of the parts of the standard way that the Science Mission Directorate operates is that all of our payloads are competed. And so, we provide science guidelines saying, whatever you think that you want to do addresses one of these goals or objectives. You're free to make your case to us. And so it is highly possible that, in addition to the geology that will be done, just by virtue of the fact that they're sampling rocks, we may very well have astronomy payloads on the moon, or, biological science payloads on the moon, in addition to the geophysics payloads that were done during Apollo.
Yeah, and I'll add to that. The Moon to Mars objectives are intentionally cross-disciplinary. So the first 4 are related to planetary science. The next 4 are heliophysics. And then there are 3 human and biological science objectives. And then there are 2 physical science and astrophysical science objectives. So for the Moon to Mars aspect and Artemis in particular, there are absolutely, like Renee said, opportunities to and a need to address all of those objectives through cross-disciplinary objectives and procedures and instruments. I'll add to that there's also, going back to CLIPS, we actually have a mission going to the far side of the moon in the next couple years to deliver a Lucy Night, which is intending to look at the deep space as a telescope. So and establish the proof of concept, I guess, for interferometry telescopes on the far side. So there are active missions to address other sciences inside of our portfolio as well. But the Moon to Mars, it's absolutely a cross-disciplinary science endeavor.
My microphone on. I think with that, we are now out of time. So I would like to go ahead and thank the panel for answering questions for all of us today and talking about science. I really liked what you said, Dr. Needham. It's an exciting time to be a scientist. So there's all kinds of stuff that's about to be discovered, and I can't wait to see what you guys come up with. So can we have a round of applause for our panel? Thank you very much.